How does multiplying affect the graph? So on this one, we're going to have y equals the absolute value of 3 times the numbers that we plug in for the x. So when we plug in -2, we're going to take 3 times -2, which is -6, and then take the absolute value of that, which will be +6. And then we'll plug in a -1. 3 times -1 is -3. Absolute value of -3 is +3. And then we'll plug in a 0. 3 times 0 is 0. Plug in a 1. 3 times 1 is 3. Absolute value of 3 is still 3. And then finally plug in the 2. 3 times 2 is 6. Absolute value of 6 is still 6. So -2, 6. -1, 3. 0, 0. 1, 3. And 2, 6. So we've got our V shape again, but notice the V shape seems to be a little bit taller and a little bit skinnier when we compare it to the rest of the graphs. So we've got the V shape there, and then as I scroll up, notice the V shapes are a little bit shorter, a little bit wider. So we do have a name for that. It is called a vertical stretch because it is taller and skinnier. So we got tall and skinny. But the math name for that is vertical stretch. Domain and range is not changed on this one. Domain is still going to be all real numbers. I can't emphasize that enough. What's the range? So the range will be y is greater than or equal to 0 because the lowest point is still 0. So the vertical stretch really did not affect the domain and range at all. Let's do a fraction now. How does a fraction affect an absolute value function? So we're back to function notation, f of x. No change on that. We're going to take the fraction 1/2 times each of the numbers that we plug in, and then take the absolute value of that number. So 1/2 times -2 is -1, and the absolute value of -1 is +1. And then 1/2 times -1 is -1/2. Absolute value of -1/2 is +1/2. Absolute value of 0, or excuse me, 1/2 times 0 is 0, and then the absolute value of 0 is 0. And then we'll do it with 1. 1/2 times 1 is 1/2. Absolute value of 1/2 is 1/2. And then with 2, 1/2 times 2 is 1. Absolute value of 1 is 1. So -2, 1. -1/2, so I got to squeeze a half of a block there. 0, 0. 1, 1/2. And 2, 1. So how did multiplying by 1/2, how did that affect the graph? And it got shorter and it got wider. We call this a vertical compression. Vertical compression. Basically what that means is it got short and fat. Or short and stocky if you want to be, maybe use a nicer name for it, short and stocky. But it does not change the domain and the range. It has the exact same domain and range as the one that has the vertical stretch because the point here, which they had a word in geometry and it has the exact same word in Algebra 2, it's called the vertex point. The vertex point right there is exactly the same as the vertex point in the vertical stretch graph. So it has the exact same domain and range. Domain is all real numbers. The range is all real numbers. There is a danger with doing t-charts on every single graph, and I want to talk about that on the next one. Again, the ultimate goal is to look at a graph and be able to graph it immediately without a t-chart or minimal use of a t-chart. If you try to do t-charts for everything, you will run into a problem like this. So we're going to do y equals the absolute value of x plus 4. So we will take each of our numbers, add 4 to it, and do the absolute value of it. So we'll do the absolute value of negative 2 plus 4. Negative 2 plus 4 is 2. The absolute value of 2 is 2. And then we'll do negative 1. Negative 1 plus 4 is 3. Absolute value of 3 is 3. And we'll do 0. 0 plus 4 is 4. Absolute value of 4 is 4. And then 1. 1 plus 4 is 5. Absolute value of 5 is 5. And then the last one. Absolute value of 2 plus 4 will be 6. So look what happens when we graph these points. I'm at negative 2, 2, negative 1, 3, 0, 4, 1, 5, and 2, 6. And it sure looks like to me that that is a straight line. But aren't these supposed to make V's? And yes, they are supposed to make V shapes. Absolute values are supposed to make V shapes. So do we have a mistake? Not exactly. We do have the correct math done, and we do have points that are going to be on the graph, but the problem is we haven't found the vertex point because we don't have the right points to find the vertex point. The vertex point is somewhere larger than the negative 2 outside of the negative 2 and the positive 2. So what do we know about the graph where the vertex point might be located? Might it be up here and the graph is somewhere upside down? And we already know that's a no, because one of the first graphs we did, when there was a negative outside, like right here, that's when it turned the graph upside down. So this is not going to be an upside down graph. So we must have the vertex point somewhere down in this area somewhere. So for right now, we just need to continue to plug in lower and lower numbers until we find that vertex point. But again, the ultimate goal is going to be that we're going to be able to do this without a t-chart. But for right now, on the assignment that you'll have today, that you're going to use t-charts. So let's start plugging in more and more numbers. So we need more and more lower numbers. So if we do a negative 3, if we plug in negative 3, will that help out? So I plug in negative 3. So negative 3 plus 4 is positive 1. The absolute value of 1 is 1. So negative 3, 1 is right here. So that doesn't show us where the bounce point is yet. So we better try negative 4. So negative 4 plus 4 is 0. Absolute value of 0 is 0. Still haven't found the bounce point. So we got to keep trying lower and lower numbers. So we're trying negative 5 now. Negative 5 plus 4 is negative 1, but the absolute value of negative 1 is positive 1, and I believe we found it. It's right there. So now we can see that it bounces, and now it's starting to rise. Don't need to do any more points because they're all going to be on this same straight diagonal path. And there we go. So that's what the graph looks like. And notice again that the vertex point has moved 4 units to the left. We may have predicted it moved 4 units, but it may be surprising that it went to the left, even though it says plus 4. And again, we'll talk about that later. Domain's all real numbers. The range, no change on the range. It is still y is greater than or equal to 0 because we did not move this vertex point up or down at all. It just moved left and right, but still has a y value equal to 0. Let's try one more. This is the granddaddy because it's got a little bit of everything on this one. So back to function notation, but we should already know that doesn't change anything. So we're going to take the absolute value, or excuse me, negative absolute value of 2 times the number we plug in. So we'll start out with the negative 2. And then take that answer times, or plus 4. So let's look to see what happens here. Give me a little extra room to work with. So I'm going to have negative absolute value of 2 times negative 2. And that's going to be negative 4. plus the 4 that's already on the outside. So the absolute value of negative 4 is 4, but this negative on the outside does not affect it. So it's still negative 4, and negative 4 plus 4 is 0. So when x is negative 2, we get a y value of 0. And then we plug in negative 1. Come on. There we go. Plug in negative 1. So we will have, need to erase a little bit here. So negative 2 times negative 1 is negative 2. Absolute value of negative 2 is 2, but the negative on the outside keeps it at negative 2. And negative 2 plus 4 is positive 2. And now plug in the 0. So 2 times 0 is 0. There is no such thing as negative 0. So we wind up with 0 plus 4, which is 4. And then plug in the 1. 2 times 1 is what? Well, 2 times 1 is 2. We have the negative still on the outside, so it becomes negative 2. Negative 2 plus 4 is positive 2. And then maybe you can pause the video and quiz yourself on the last one. What do you get when you plug in 2? So we have 2 times 2 is 4. The absolute value of 4 is 4, but the negative reverts it back to negative 4. Negative 4 plus the 4 that's on the outside gives you 0. So negative 2, 0. Negative 1, 2. 0, 4. 1, 2, and 2, 0. So we have the negative that flipped it upside down and gave it a reflection. We have the positive 4, the plus 4 on the outside that moved the vertex point up 4 units. And then we had the multiplying times 2 on the inside of the bars, and that wound up stretching it. So it was a vertical stretch, got shifted up 4 units, and then reflected because of the negative sign.